Good afternoon, everyone. We're just going to give it 2 minutes before we start the session today. We'll just give it 1 more minute to enable everyone to join, and then we'll start the session. Great, we might get started. So thank you very much, everybody, for taking the time to join us this afternoon. My name's Juliana Smith, and I'm the Energy Transition and Sustainability Lead for Bureau Veritas. We've got a really interesting topic for discussion this afternoon, which I think is very critical to the energy transition here in Australia. Like all technology, wind energy assets have an operational life, and a significant portion are starting to reach that. Owners and operators are asking themselves how to make the most of our wind resources, and we've learnt that taking a proactive approach to asset life extension and repowering is critical. Today, Partha is going to provide some context on the global and local Australian market and outline key considerations when looking to maximise your wind asset potential and the critical factors to be considered during asset life extension and repowering. Just a brief bit of housekeeping before we get started. There are a few things that I want to cover. Partha is going to be presenting for around 45 minutes, allowing for 15 minutes of Q&A at the end of the session. The session is going to be recording, and the recording will be shared with you after the webinar. If you do have any questions throughout, then just drop them in the chat box and we will get to those at the end of the session. And if you are experiencing any technical issues, then let us know in the chat box and someone will try and help you. But most importantly, we hope that you enjoy the session today and find it very valuable. And for those on the call who don't know much about Bureau Veritas, we are actually a world leader in laboratory testing, inspection and certification services. So we were created in about 1828. And the group has 82,000 employees located in more than 1,600 offices around the globe. BV helps our customers improve their performance and risk management by focusing on how they mitigate their quality, health, safety, environmental protection and social responsibility. We've got a long history in renewable energies with experience across all the different technologies, and obviously wind is the main topic of conversation today. Partha is based within our local renewable team here in Australia, and I'm very pleased to introduce him today. He's a key member of the team with over 14 years of experience based out of our Brisbane office here in Queensland. He's a mechanical engineer with a lot of experience in rotating equipment and turbines, and is active and passionate in this space and one of our excellent technical specialists because his ability to deliver pragmatic advice to our customers, which is why we love him. So on that note, Partha, I'll hand it across to you.
Thank you, Jules, for introducing me to the wider audience. Hello, everyone. My name is Partha Ravi. As Jules mentioned about my background, I joined with Bureau Veritas under 6 months, and prior to joining Bureau Veritas, I've been in the wind industry for more than 14 years now. I have worked across in the design space of wind turbine simulations, and also finite element modeling of major component structures, and also in the gearbox space for doing certification process for the new gearbox designs. So that's in a nutshell about my background. I would proceed with the slide deck. In today's topic, which I'm going to cover, is about how do you interpret extension of life extension of the wind farms, and what's happening in the global context, what's happening in Australian context, and then we would walk through the process of life extension in terms of how owners can make decision process in strategizing in early stages, whether you want to do a repowering, whether you want to do a decommission, or you want to extend the life of the turbine until decommission process. So in what we have learned in the European sector as well as in the North American sector is that from the reports that has been compiled by Global Wind Energy Organization and Wind Europe, they mentioned that the wind farms which have been commissioned in early 2000 and since up to 2010 started coming into a phase of repowering as well as lifetime extension, and also some of them are also getting into a decommissioning phase. So the aggressiveness of this lifetime extension is not only happening uh, here in Australia, but then it's been in particular been looked at in Europe, how the governments are supporting the owners in realizing that their existing wind farms could be better off for repowering rather than decommissioning. So there is a both contexts will be discussed. So if you look at the complete scenario, there are about 40.9 gigawatt of onshore wind farms that has been installed. And typically all these 40 gigawatt of wind farm has got a 2 megawatt and 1 megawatt typical nameplate rated capacity of wind turbines. And at the most, Germany, followed by other European countries, are in the lead up to look at the repowering or life extension situations. Now, when you look at what's happening in the Australian context, we see that in the next 10 years' time, or even 8 years' time from now, we have different categories of wind farms that are coming for end of life point of view, considering or assuming that they are 20-year design life. So when the commission year was set between 2002 and 2010, we could see that these are the list of wind farm owners whose wind farm will be coming for LTE scope. Now, as I mentioned that what does life extension point is, whether we want to do a repowering or whether we want to do an extending the life of the turbine or whether we want to decommission. But we have to look at what is the context of this going for a life extension process. Some of the owners are realizing that they want to have a decarbonization targets. There is also an issue with respect to waste recycling after decommissioning. How are we going to handle that? What are we going to do with the blades which goes to a landfill? Is there a process to retrieve and reuse them in a circular economy? And also the recent pressure of supply chain due to the cost, availability, and product evolution in a short span of time. It's much like you have a hybrid car and an electric car, and there's a rampant use of usage of electric car, and there's a push for use of electric cars. So, but then the market is not well prepared if you see in that context. So similar kind of issues is also existing with the turbine technologies growth. Now, LT has not doesn't have a proper IEC guideline, but then it is in being the draft stage that has been proposed, and it's been possible it would be released this year. Bureau Veritas has its own LTE guideline that has been vetted by a leading technical centers. And we released our first Bureau guideline in 2017, and the latest version was released in 2022. So what we covered in this guideline is that it's not only for onshore turbines, but it is also for offshore turbines. Now, when you look at the concept of a life extension, what exactly it means is that there is a design lifetime when the turbine is actually produced before the commissioning stage, and it has an option for 20 to 25 years for an onshore, typical onshore turbines, whereas for it would be for offshore between 30 to 35 years in the design lifetime space when the turbines are designed. In the context of what the extension it means is when it is reaching 20 years or 25 or 30 years, how much can you extend when it is reaching its end of design life, and how much can you still use the existing structure to keep producing the power. The question then it comes is again to the concept of whether you want to go for a repowering or a decommission or extension of life with what you have so far from your wind turbine productions. Right. So in this first slide of the lifetime extension, I would be walking through the repowering of wind farms. Why do we need to consider repowering? How does these strategies help to owner to decide at a very early stage when do you want to repower it? What are all the considerations and strategies you need to look for? So when you look at complete life cycle of the wind farm or a wind turbine, from commissioning of date all the way up to the year 30 or 35, we would see in terms of repowering whether the owners could make a decision how much is the capacity of at the time of commissioning, how much more is also available for the future. In the sense, for example, if you say pick and choose a particular wind farm at a particular site, and in the future there is no augmentation of grid capacity, then there could be a low chances that you may not be able to extend the life, or you may have to go for a decommissioning process. On the other hand, if there are feasibilities that okay, the site has got a higher dispatch capacities, and there is a chances that you could look for an LT assessment, that then in this situation in year 10 or year 15, you could possibly evaluate whether you can go for a repowering scenario. In the next couple of slides, I would talk in detail how repowering concepts are looked at and how it has been evaluated in Germany for a specific case. And there are some tests and trials that have been also made for repowering cases. The other aspect is like once you have reached in the later stage of the design life of the turbine in year 15 to year 25, this is where the actual assessment of LTE starts. So you may have crossed your break-even period from repowering to even using the existing turbine to extend its life and decommission it. But then in some case-by-case scenarios, the repowering could also be done in this stage so that you are much ahead of in time, let's say 10 years or 5 years, and use the existing wind farm facility for a repowering case. Now, this particular slide shows that what's the actual scenario of wind turbine technologies that has been used since 1999 all the way up to till 2023, and some of these wind farms are coming up. So this linear graph, which is going up all the way, where the first earlier turbines were all 0.6 megawatt, 1.8 megawatt, 2.3, and that's the class of turbines that landed up in Australia back then, some 15 to 20 years ago. But when you look at those sites, they are all classified as a golden sites. The reason it's a golden site is the reason it's at that time you had a best in class for those sites. You had, but then the turbine technologies were not up to speed. But now, when you see till date, you have 6.2 megawatt. One turbine itself is able to produce 6.2 megawatt nameplate capacity. They have options to even upgrade or degrade the turbine on the same using the same platforms. There is also talks about introducing 7 megawatt onshore in the long run in another 4 or 5 years. There's talk about even getting a 9 megawatt platform onshore. But then there is again, feasibility is going on whether in which areas those turbines would be suited. You may run out of space for those turbines, not able to suited for these kind of wind sites. So if I look in let's say the picture on the left is on the first two rows is your existing wind farms, and you have 2 megawatt capacity of each turbine. You may have capex and opex cost going on till the end of life. You may have retrieved, you may have a situation where you have paid off the complete cost of the turbine. The owners don't have to worry about any upfront payment apart from opex costing. On the other hand, if they would reevaluate the same site, they could go maybe from a 2 megawatt to repurpose the site for a 4 or 6 megawatt class turbines. But these steps need to be taken a bit early on, where you could validate what is your cost layout in terms of how much you are expending your OPEX cost. Is your turbines consuming more cost to produce the turbine per location? And how is the access to your existing supply chains as against your new turbines, which would be much more efficient than your old turbines. So we have looked at the Australian context. We have seen that there's been no repowering so far carried out in Australia. The reason is that like regulatory support, it could be one of the reasons. The other reason is that the connection capacity in older sites are not permitting that dispatch or the grid facility is not sufficient enough to push to the limits. Third point is looking at your communication systems, how your underground communication cables have been laid up, have they been up to date from 3G, 4G, and upgrade to 5G, those kind of issues. Then the other issues are your local support government to accept that whether the new turbines could be accepted in the same location. So there are two aspects to look at. One is financial perspective and also social acceptance.
Yeah. So Partha, sorry to interrupt,
yeah.
just very quickly. So you mentioned, one of the critical aspects here is around planning and timing. When do you think is the best time to start thinking about some of these strategies?
So repowering concepts could be even looked at as early as when you're even signing up your contract with your OEMs, even before the wind farms are set up. So early stage developers could think, okay, because it's a always on the go wind power production capacity of a wind site location, how best you could utilize that. For some, based on each owner's decision process case by case, for some people, it would be advisable to have an information at early stage and then relook at it at year 5, and then possibly proceed to have it commence the repowering if it all turns good in year 10 to year 15. So in that way, the timing would be much better. You could have a staged approach where you have an ongoing capex and opex, and then you have a new influx of capex and opex as well. So these are the ways at which you can look at it.
Thank you.
Yeah. Right. If everything goes well in terms of social acceptance, the local support by the government, and there is infrastructure capacity, The strategies of looking at repowering is like, let's say you have one collector group of turbines which are consuming more OPEX cost than your rest of the wind farms, and you have the repowering case well sorted out from your cost benefit point of view, from your investors point of view. Then maybe it would be like worthwhile to look at, okay, first let's decommission the first set of 10 turbines in a collector group and then replace them with a new set of turbines. It may seem very straightforward in terms of talk, but then yes, in terms of assessment, there are more things to look at it. So what we need to look at it is whether you need to go for the new turbines, shadow flicker assessment, aviation assessment, permitting process, transport and logistics, how far the new turbines are able to cope up from your existing shipyard all the way to the same location. You're doing both things at the same time. One is decommissioning your existing turbine, and also in a matter of time, you are preparing your land for your new turbines. Some companies or owners in Europe are also trying to see that if they can use an existing foundation itself. For example, let's say you have a 4 megawatt class turbine and the foundation size will be 6 to 10 meter in diameter. Can the same foundation could be used or repurposed for 4.5 or a 5.5 of the class of turbine. Now, I would like to jump into the context of a life extension, what exactly in the life extension process would look like, where what you need to, I would walk through the process and then look what information criticality you need to be gaining from your OEMs. If you have your wind farm 20 and 25 years old, and you don't have a lot of information, then it would give a lot of more uncertainties, and then more inspection activities has to be carried out on the turbines. Then I would walk through how the turbine design life 20 and 25 is arrived. Based on that, how you are extending the turbine life is what I would walk through. That's the core key aspect of this webinar. And then how do you interpret P50, P90 results? How do you look at fatigue damage loads? What happens when there are cracks, visible surface cracks on your major components, such as like mainframe or a bed frame, or even on a hubcast? And then when you are in the end of the process, you have a condition assessment strategies and maintenance strategies prior to decommission phase. So basically, a life extension is to look at a component where it is doing the load transfer from the rotor loads onto the major components. So the major components like main shaft, gearbox, and generator, which are replaceable, but then there are non-replaceable components like your hubcast and mainframes and the generator subframes. So, and also the tower. So we would be evaluating those cases. Now, Bureau Veritas has its own, from the guideline, we have a 3-stage process, which tells about whether you want, based on the level of information, what we have from owners, we would categorize, okay, what context you're looking, whether you want from preliminary study point of view, whether you at what stage, whether you want to go for a repowering or life extension or a decommissioning phase. Based on those information processing, initial information processing, we have an option on stage 2 to do the analytical process as an overall, and then followed by a condition assessment, and then give you a final evaluation, which is a confirmation certificate saying that these turbines could be extended from its end of design life 20 or 25 to maybe 6 years or 8 years in operation. So, as I mentioned in my previous slide, the differences of preliminary, analytical, and condition assessment, what exactly the scope would look like is what are the contexts information what we are capturing, what is the regulatory context, what are the current environmental conditions the turbines or wind farms are placed into. Then into the analytical phase, we would be trying to using the information try to compare what's the site wind load conditions to the original design the turbine was intended for. And then we use an aeroelastic model, which is again in the initial phase of the turbine design itself, the aeroelastic model would have been created, but then it's not easy to get those kind of information from your OEM. So it becomes again as a gap analysis to rebuild this same aeroelastic model and then come to a conclusion, what's the life left? The other aspects is looking at the turbine criticality and also the fatigue life, which rules how much life is left structurally on your turbines to perform. Then comes the case of condition assessment, where based on the analytical study, we would come to a conclusion how many turbines have to be actually visually inspected or even has to go for an advanced NDT methods of testing. And then it would also look at your foundation assessment, whether you need to do an NDT assessment without making, digging out your foundation to see exactly what's happening. We have new methods to evaluate the foundation. And then in the final stage, we would give a report which would consider what methods have been considered, what are the uncertainties, and then condition of the preparation, maintenance plan from the condition assessment all the way to the decommission process. Now, looking at the overall methodology or overview, as I mentioned that we gather documentations, I would list in the next couple of slides what kind of documentations or criticality information we look at. Then what kind of data we prepare for the aeroelastic model, and then make a judgment of remaining useful life. This could also be not only fatigue load assessment, it will be also in the context of a reliability assessment. Some owners may have this data saying that, okay, I have an OEM's forecast of OPEX failure data. Could we be able to give a forecast how much time can this reliability assessment could be performed from your existing design life to the life of failure? From that, we would be able to prepare P50, P90 results, and then come to a conclusion of component criticality. Now, as I mentioned in the previous slide, if the approach of information with the owners is less, then we may go with a basic approach. But then in the context of inspection point of view or the efforts for us to come to a conclusion saying that how many life or expected years is there, we may not be able to give you a confirmed logical reasoning saying that can it sustain beyond 2 years or can it sustain beyond 3 years or 6 years. Basic approach would limit us those kind of efforts. But when we have more information from reliability or probabilistic based approach, or even standard approach. So there's a difference in standard and detailed approach. So in the standard approach, we would have more information gathered from the owners, which would be sufficient enough to gain the knowledge of what's the actual model of the turbine that has been built on and how realistic our results are getting close to the original design was. In comparison, the detailed approach, we would be even having more information like control system strategies that has been performed on the turbine, what all the changes that has been done, which is affecting the turbine loads. So the more the information, less is the effort for us to predict the LT results. Now, as I mentioned, what would be the critical of information that we would require? This is a case of a type certificate that is generated when your turbine has been designed. Bureau Veritas also delivers this kind of type certificate when the turbine is designed. And we would have information that is published, trying to say when it has been, what conformity hasn't gone through. So when we ask some of our owners, they say that they don't have an access to this type certificates. Back then, 10 years or 15 years ago, the digitalization process didn't take place much well, where the information was not readily available public. But then what has happened is in the new system in the last 10 years is we have IECRE, it's a public domain website, and talks about which are the turbines, which what has been designed has got which class of type certificate and component certificate. So when you look at this particular case here, it shows that it's a Vestas V117 4 MW class of turbine. And also they've used the same platform to design the 4.2 MW class as well. The information, all this kind gives us more a realistic approach for us to remodel when we are looking at from LT context point of view. Now, looking at this point, there are more variants here. And what is the type of information in terms of the model that has been used is what this information tells about. Now, if you go one step more, we have more information in terms of where the supplier, which component has been supplied from where. Has it been manufactured in-house or from an external party who are all type certified, component certified as per the requirement? This is like a certification body requirement. So these information gives us a complete scenario. Has there been design defect issues or what? And then we would be able to, from your current design life, we could be able to tell, okay, where it is going to. Now, the other aspect of looking at your site and design is like the assumptions when we make in the design simulation process is like your air density or all these parameters would be as per the guidelines or the 61400-1 IEC standard. But when we look or evaluate the ground reality, it could be a bit different. So we need to see, okay, build this gap and build the uncertainties in this and come to a conclusion. What's the actual structural behavior of the whole turbine? Now, this is the core part. How do you validate your structure? So I'm trying to give you a context in terms of this example. The picture on the left is a person who is running a marathon once in a month, and all his limbs are as normal. But on the picture on the right, we have a person whose limbs have been replaced with a prosthetics, and he's utilizing a structure trying to run for the same marathon. So what would be the difference? And if we want to remodel in this kind of situation, we have obstacles for them in between these kind of obstacles like desert conditions, icy or elevated conditions, flat terrain conditions, or they could be doing a lot of high jumps on their way. So these are the obstacles they could be seeing. So in terms of the loads which they would be seeing on their knees will be different to what this person would be looking on his prosthetics. Now, looking at the other context of validating a structure is, in the olden days, the cars were not as safe as what we would see today. And if you look at the example of Formula One, so their purpose was to make sure that they are 10 years ahead in terms of validating how our structures are safe enough for people in different scenarios. So the cars, well, the Formula One cars doesn't go in a passenger segment. The main reason what the Formula One is designing the cars is to make sure that what are the materials they have used. Let's say the monocoque design of this cockpit is able to sustain the crash of in the event of a crash. This person is able to still survive, walk out of this cockpit. They look at, okay, if the tire is going off, even if the suspension is breaking off, or even any of this ailerons are breaking off, still it doesn't is of a major concern in its whole turbine design life. Your major design life is to make sure the center structure is good enough for its intended design, be it 25 or 20 or 30 years, whether it's able to cope up different kinds of loading situations. For example, in this case, when a braking or a turning forces are in place, the typical G forces that a person would see is a 4 to 6 G. And an aircraft or a fighter pilot would be seeing a 9G force. That it means then the same 9G force is also coming onto your structures. We won't see those kind of loads on a turbine, but then we would see a different kind of loading situations in what I will show in the next couple of slides. Now, I've been mentioning quite often about aeroelastic simulation software. So Bureau Veritas has its own software called Opera Tool, which can do both onshore and as well as offshore, covering all the structures for its assessment for design life, as well as also producing for a type certificate point of view. The other simulation softwares are FlexFi, which is not a user interface type. It's built on coding only. The NRL has also its own version of it, but it's not as good as in a commercial space. FlexFi has been used since almost like more than 30 years now. And the other version, which was released late in the 2010 period or to the 2005 period, was GH Bladed, which has got a also a user interface in comparison to BV's Opera Tool. Now, if you look at the whole context of this life extension, where are we fitting the aeroelastic simulation model? And the process is that in the early design phase, when you select a turbine or a site, we would be giving a type certificate. And this type certificate is supported by design evaluation, aeroelastic simulation code, manufacturing evaluation, all these processes. There is quite a bit of more. I have just restricted to the key aspects of here. And once the type certificate is issued, you have manufacturing conformance, and you have the turbines manufactured, and it goes for site-specific conditions. From an operational or end-of-life design life point of view, the same type certificate information, if you have, would also give us information about aeroelastic model, what all the things that has been considered, and what all the information that we would be asking the existing owners of a wind farm whose turbines are coming for a life extension. Let's say 6 years from now, you have a LTE period coming up, so we would ask these kind of typical informations. Now, the first and foremost question when you look at the early design is that, like, how did you arrive 20 years or 25 years in first place? Going back to this picture, which was done in the year 1990, it tells that the aircraft were more fatigue critical structure back then. So what does it mean is that, like, they had to simulate turbines on an not the turbine, but the components of the aircraft in an experimental process to make sure that the materials that are being used in the aircraft design, like say fuselage or the wings, are able to cope up with different loading conditions. So they used to do an experimental back and forth loading test of a fatigue loading test. Now they realized that not only aircraft is a fatigue critical structure, but then the blade, which had a change in its material from using a balsa wood in 30 or 40 years ago, then it changed to using steel structures, lightweight aluminum structures, and then it went into a process of composite glass fiber being used now. So those composite glass fiber had to be validated for a 30-year period or a 20-year period, which defined the usage of 10 million cycles of fatigue loading in the off-late rules, IC guideline rules. So this is the defining process, which states how you arrive at a 20-year or a 25-year process. Now, the other aspects, as I mentioned, was looking at the safety factors and what's the fatigue life itself. And how do you look at a fatigue life? Now, in the previous slide, I mentioned a lot of simulation cases, how we use a type certificate. One of the type certificate information is usage of your simulation loads. Not all the simulation loads are actually looked at from lifetime design point of view. We would only validate where there are transient loads, where there are change in yaw misalignments, and there are only specific cases. So this particular information, the simulations had changed from 2005, what has been done, to 2019. The other aspect in considering the life extension input information is your wind class, wind information. what has been earlier used in the design context and what has been now. So the picture on the right is the latest one of information from 2019 guideline, where they have also included the tropical wind zones locations. So what does it mean is that we have turbines which have to cope up more extreme loads than what you have in the current wind locations. The other turbines which are having issues when they're in their operational design life is looking at their warranty issues, foundation issues. The other aspect is also looking at the upgrades and the wind conditions, or any WSM optimization has been carried out, or it has not been looked at all for the 10, 15 years. The condition assessment or LT repowering, if it has to be done in this year of its turbine life, then there could be cases of tower tilting. Some may not observe if the condition assessment has not been carried out properly. There are cases where blade separation could have happened, serial design defects could have happened, which would have been inside the turbine, but one may not have realized it. And the other aspect is looking at your usage of your electrical balance of plant components and also some of the components inside the turbine. So AEMO has utilized or classified turbines based on type 1 to type 4. Type 1 and type 2 are classified turbines where less than 2 megawatt, some of the old turbines are having issues with grid compliance. So they don't perform very well with respect to what is the latest grid issues are. So the new generation turbines are much more compliant and are able to do the frequency fluctuation in transmitting the power from turbine all the way to the main grid. So those are the differences we are able to see, or the issues that are cropping up when throughout the turbine design life. Now, this slide is information at a high level, what exactly we need in an aeroelastic model, what are the components we consider. The more the components we have, the information, the better the realistic. Be it whether it is a 1 megawatt, 2 megawatt class of turbine or a 9 megawatt class of turbine, the aeroelastic model is created for every type. Now, when we look at what is the information that we need, is at a component level, we would be going for all these major components. When we even have a more detailed approach, then we would even go for a like getting the mass and inertia details or a gearbox, not up to the level of the components, but then what is exactly their mass and how well the structure is. Jules, I just wanted to know how much time is left. Am I keeping in time so that?
You're running a little bit behind, so it's 1:43 at the moment.
Right, maybe I have 6 more minutes to cover up and then talk about
questions
this next
for 10
couple
minutes.
of slides.
Yeah, 10 minutes of questions
right.
at the end. Yeah.
Yeah, sure. Right. So as I mentioned, what we gather from an aeroelastic simulation model from a design perspective is to build a model which never existed. So we gather these kind of informations, such as we have to build a design load cases. We have to see from a structural and fatigue loading point of view, what kind of material are we using for major components? What is the system's behavior and redundancy? And also the external class of conditions from the turbine's behavior point of view. When coming it to from life extension point of view, we would derive the same aeroelastic model, but then we would look the data in a different perspective. So we wouldn't be asking, give us a design load case, but then it would be looking at wind site load cases. And also what is the specification that has been used? What is the SCADA system for the last 1 to 2 years? And what measurements have been performed in its lifetime. The major inputs, as I mentioned, for getting the remaining useful life on the right-hand side will be, these are the key aspects which would be asked. One of the aspects is also to looking at your site turbulence intensity, or what has been at the, your current site to what has been designed purpose site. Looking at your SCADA aspects, how many turbines have been derated, what is the purpose, how many times or cycles in a year this derating has occurred, and has it got any damaging effect on the structure itself. So these are the kind of information that we would be able to correlate to know, ascertain what's the structure's condition, current structure, and then we would be able to generate an information how much life can it still go on, and when to decommission it. So this is another aspect when we say that what's the existing extended design life would look like, and what P50 in terms of fatigue calculation would look like, and P90 load simulation in terms of extreme load calculation would be considered. So in these aspects, when we combine, we would be able to say what's your component by component situation. Now, I'm going to talk just close about this. This information is that, okay, given a damage scale of a hub cast component, generator which has been welded, and also a casted mainframe. So what does a damage scale means in a fatigue life is between a scale of 0 to 1, if the indicator is towards less than 0.3 to in its whole 20-year life, then it has got a better RUL. But in the case where the RUL, the damage classification is for the structure, main structure, which is non-replaceable, is above 0.4 or getting to this range in its 20 to 25-year life, and we ascertain that this is the current condition, then your RUL could be even lower than what the design life could be. In the other case where the damage classification is more than 0.6 or 0.8, it means that the visible crack starts approaching in these two cases, and you would be seeing more visible cracks on your structures, permanent structures, and that's not a good sign in terms of turbines operation point of view, and thus it leads to a lesser remaining useful life. So that's the aspect at which we look comparing a fatigue life to a remaining useful life. The other aspect is looking at some of the recent trends we have seen is that using multi-direction load, but most of the lifetime assessment is done only on a uniaxial loads. So this has been also been under evaluation and has been considered under the new IEC guideline. So the picture on the right is something about a SN curve that is for a particular component and a slope code of 3. So every component, be it blade, main or a steel structure, we have these aspects. What is the design life and what is the remaining useful life is what we would be interpreting from this SN curve. There are uncertainties as well. So those uncertainties are like how much the detail of information, what we have assumed, and what are the load cases that have not been considered. Based on that, these uncertainties would be looked at. So when you look at the picture on the right, you would have how much the failure percentage can go up and up as the turbine ages beyond 20 or 25 years. Now, the last aspect of this webinar would be looking at the component criticality. As we have assessed the analytical information, we would, let's say if you have a 100+ turbine or a 500+ turbine, then you would not be able to do a 100% visual inspection. So the assessment would rely 90% on the analytical results to ascertain how much LT inspection, component visual inspection you need to carry out. So we would have something like a criticality index like this for every component, and then would rank based on that what's important, what's the best, and what's the worst. And we would come out with an inspection type for each and every type of component. In some places, we are also started using blade internal drone inspections for blade as well as towers, which fast tracks the way in which we look at the visual inspections. The other aspects, this is a kind of a good information to look at right from your foundation all the way. What exactly is covered in a condition assessment is your foundation, your tower, your welds, how good use your blade health conditions in terms of its cracks. Let's say at year 20, we are ascertaining this. We could look at your maintenance and inspection records. And then if there are cracks on your foundation already, then what mitigation you have to do. How much will it be able to sustain? We have cases where a gearbox failure, even let's say one or two gear tooth has failed, is not so important as compared to a crack that a mainframe can look at it. So a mainframe crack is more severe than what a gearbox failure could look like. In this case, you would be able to replace a gearbox, but not the frame of the gear turbine, which is holding the gearbox. So that becomes a more critical aspect. We would ask you to increase the frequency of that inspection, how much loads are passing through the turbine, is the crack growth is increasing substantial year by year. So those are the aspects we look at it. Now, when we look at the final part of my slide is what is the failure modes. And for each and every component, we don't want to see a blade rip off while it is in year 20 or 25. This owner would try to protect that their turbines are well received and well accepted in the public space. Safety commissioners keep a watch on what's happening to your wind farm, be it here in Australia, where there have been even cases where at the start of the commissioning of the turbine itself, the blade had cracks. Or this is a case where the worst case scenario where the blade root bolts have ripped off and it had strewn across the field. So these are the kind of situation is a worry for owners in if they are being an owner operator situation. Now, coming to the conclusion part is what we would ask wind farm owners is talk with your OEMs and ascertain every 5 years what is your current situation of your turbine life, how critical is your supply chain, evaluate the cost point of view, look at your minimum set of information that you need to gather. As I showed in my presentations earlier, at least having a type certificate, a lot of owners aren't aware what exactly a type certificate is, what is the relevance of it. Most people are not aware about the certification process. And also in some places, there is a gap between OEM not sharing those critical piece of information from design or drawings due to the confidentiality. The recent information has been, all this information has been compiled in IEC guideline to ascertain or help with the owners that what information you would be requiring and how to interpret. If not, you would see guidelines from every certification body coming up asking different ways of information. The other aspects, what some of the largest wind farm owners where they don't have any kind of information is that they rely on digital engineering or digital twin to ascertain can we do this lifetime extension using digital twin modeling and ascertain what's the life left out when there is no information at all. The other aspect, final aspect, is the new turbine technologies have more information that is being protected and not shown. This is because of competition between the OEMs trying to get the best out of their turbines and the best places. So the information gets more obscured, which puts more issues in the later period when it is a lifetime extension situation scenario. So that's the overall context of this LTE. I believe you would have been able to gather or grasp the core of the information, what we exactly look in terms of your the turbines aspect is to make sure that the turbine is structurally integral until the decommission is happening and is able to fruitfully deliver your power production. That's the end of the slide.
Great. Thank you, Partha. I think it was definitely informative and provided a lot of insights for the audience. We actually haven't had any questions come through on the chat. So given that it's 5 minutes to go, oh, here they come. We do have a few questions. So Partha, I'm not sure whether you can access the chat or you would like me to read them.
Yeah, that would be great. Go through.
Okay.
Yeah. If the component surpasses theoretically expected design life but remains structurally intact, what steps should be taken to assess the remaining life? So if that's the case where we interpret that based on assumptions that it has been crossing the design life, then we would ask to perform more NDT visual inspections to exactly maybe even we could also do a strain gauge testing whether the fatigue loading has really crossed or not. Those are the aspects we would see to validate whether has it theoretically crossed or not. Yeah. Could you please talk more about foundation assessment? Obviously not limited to the foundation can be visually inspected. Yes, so the foundation assessment. So recently what I've learned the growth of technology is that there are ground penetration radars being used where you don't have to excavate any part of the foundations. So some places are using the foundation in terms of to see whether can it cope, the same foundation can it cope for a new generation of turbine. Let's say I'm having a 3 megawatt or an older class site has got a 3 megawatt class turbine. Can it be repurposed for a 3.5 or a 4? The same foundation, can it withstand? What all changes do I need to reassess that? So those kind of information, your existing OEMs itself can give an answer to it and also be independently validated by certification body like us to give you a confirmation or assurance to your investor. Yes, going from a 3 to 3.5 and you're completely replacing with a new class of turbine on the same foundation is a viable solution or not.
Okay. Excellent. Thank you very much, Partha, and thank you very much for those excellent questions. We might close the session there. Thank you very much for spending the past hour with us. And as I mentioned at the start, we will circulate a copy of the webinar for those who have attended. Thank you.
Yeah, maybe we should also add that they can reach us out and get to know more clarification on case-by-case basis. What is your existing wind farm condition? Whether you're looking for a repowering or you're trying to extend the life, we will be able to help that in that space.
For sure.
Yeah. Thank you all for joining this session. Please feel free to buzz me on LinkedIn or directly on my email ID, which will be reissued once after we close this webinar.